Good afternoon to everyone. So I am Jean-Marc Tulliani from Politecnico di Torino, and I will talk this afternoon about a different topic with respect to what we have heard this morning, because we will talk about the dispersion of carbon nanotubes in cementitious materials. This will start the session dedicated to self-sensing materials, most of them based on carbon nanotubes. So this is why we will talk about the importance of the correct dispersion of these materials into cementitious systems. So first of all, a quick outline of the talk. So we will see why it is important to, or rather, what do we expect from the dispersion of carbon nanotubes into cementitious materials, and then we will see why it is important to reach good dispersion into cementitious materials, but of course not only in any other material where you want to disperse these carbon nanotubes. Then we will also talk about how to disperse these carbon nanotubes, and to this aim we will talk also about the functionalization about these materials to help the dispersion. And finally, of course, we will have to evaluate at a certain point the quality of the dispersion we reached in our work. And finally, we will try to draw some conclusions about this dispersion. So first of all, just a few words about carbon nanotubes. I know you all of you know these tiny objects. You know that there are basically two kinds of carbon nanotubes: the single-wall carbon nanotubes, where we have only one roll of graphene sheet, and then you have the multi-wall carbon nanotubes, where you have different concentric tubes together. Of course, the dimensions of these objects are different. If you have a single-wall carbon nanotube, of course, the diameter will be much lower respect if you have multi-wall carbon nanotubes. And so, as you can see on the slide, the sizes and the diameters of these carbon nanotubes can be very different. The aspect ratio of these carbon nanotubes is approximately 1000 in general, but it can be much higher. Of course, it depends on the synthesis conditions. Then these carbon nanotubes, as you know, also have outstanding mechanical, thermal, and electrical properties. So the idea when reinforcing any kind of material, not only cementitious systems, but also polymers, and also ceramics, some attempts have been done. We also into ceramics with carbon nanotubes. Of course, the idea is to transfer these outstanding properties to other systems, and at that point it is important to have a good dispersion of these tiny objects in any kind of metric, whatever it is. So the chemical bonding of carbon atoms is composed mainly of sp2 bonds, which that are similar to those we can find in graphite. These bonds are much stronger than the sp3 hybridation we can find in graphite, and so this makes the carbon nanotubes with high modulus, high elastic modulus, and of course high strength. So it is expected that the tensile strength, for example, of single-wall carbon nanotubes can reach 500 gigapascal, one order of magnitude less for the multi-wall carbon nanotubes. But anyway, these tensile strength values are much higher with respect to most of the other materials. Young's moduli, of course, for this kind of nanotubes, either single-wall or multi-wall carbon nanotubes, are expected also to be much pretty high, about 1 terapascal for single-wall carbon nanotubes, and 5 times lower for multi-wall carbon nanotubes. At the same time, the electrical conductivity, because of these sp2 bonds, is very high for both either single-wall or multi-wall carbon nanotubes. And then the electrical properties are, of course, sensitive to the presence of impurity atoms and of defects in the structure. And finally, as we have seen during the presentation of Gabriele earlier during this SmartThings meeting, the electrical resistance of carbon nanotubes is sensitive to stress and to strain, so we can obtain, in this case, piezoresistive materials, so materials that are able to sense either stress or strain. Then if we talk again about these carbon nanotubes, just a quick presentation of one of their features, and in particular it is referred to the chiral vector, which is this vector there, which can be defined considering a reference system made by these two vectors, A1 and A2. So we can define this chiral vector considering T, which is the direction according to which the graphene sheet has been rolled. So not necessarily the hexagonal cell of the nanotubes remain in the position you have there on the screen, but of course this position can withstand a certain rotation. And at that point we can define this chiral vector, which can form a certain angle, which is called chiral index there. And this value of this angle can range from 0 to 30 degrees. Then if we use this kind of reference vectors, A1 and A2, we can define the chiral vector as equal to n A1 vector plus m A2 vector. So n can be equal to m, but it can be also it can have also a higher value. At that point, these indexes are important for the optical, the mechanical, and the electrical properties of the carbon nanotubes. And for example, if n is equal to m, or if it n minus m, and if we take the absolute value of this n minus m index, and if it is proportional to free I, where I is an integer, the nanotube is metallic. So from conducting an electrical conducting point of view, it's a perfect metal. And at the same time, if n minus m, the absolute value, verifies this second equation, the nanotube is no more a metal, but it behaves as a semiconductor. And these two conditions are the ones that are normally found in single-wall carbon nanotubes. And then for multi-wall carbon nanotubes, again, there is a different relation, the one you have there on the screen. And if 2n plus m is equal to 3i, with again with I an integer, the nanotube behaves as a metal, and otherwise it is a semiconductor. And you find this situation where you don't have the configuration there, where n equal m, and you have what is called the armchair configuration, where, as you see, the position of the hexagonal cells. And also here you have m equals 0. As you see, there is a different position of the hexagonal cell, and this is the famous zigzag configuration. Both are related to single-wall carbon nanotubes. And then you have a twisted configuration with the, as I was mentioning before, with the hexagonal cells that rotates, and you have the chiral configuration, which is more specific to multi-wall carbon nanotubes, and at that point the indexes are no more equal each other. Then, if we know these parameters, n and m, we can calculate the diameter of the carbon nanotubes by means of this formula, where you recognize there the two indexes, n and m, and you have also here the distance between the two carbon atoms, which is known, and it is equal to 0.142 nanometers. And then you can also calculate the chiral index, theta ch, which is arctangent over the multiply the arctangent of these values of the n and m parameters. Then, now that the presentations have been done, why it is important to reach a good dispersion of these carbon nanotubes into cementitious systems, because we are talking about these systems, but we could also say the same thing for polymers, for example, if we wanted to disperse the CNTs into a resin. So normally what one expects when we disperse these carbon nanotubes into cementitious systems is that we observe, hopefully, an increase of the compressive or of the flexural or of the tensile strength or even the elastic modulus. Of course, if we disperse this carbon nanotube, is to improve the properties of our cementitious systems, and of course we don't want to worsen their properties, otherwise this is not necessary to work so hard for dispersing these materials that are also quite expensive materials. So of course, if we do this dispersion, we expect to have better results with respect to a system that doesn't contain any carbon nanotubes. So as you can see there, in this review, the authors plotted the results that were found in the literature, where you can have, in function of the carbon nanotubes that were added to cementitious materials, the improvement for the green points, or the decrease of the compressive strength for this cementitious system. So as you can see, sometimes it's possible to increase in a very important way, more than 100%, the compressive strength of cementitious materials after the addition, in this case, of 1 weight% of carbon nanotubes. But also in other cases, it was possible to worsen by more than 40% the compressive strength of the system. And of course, all these red dots are connected to a non-good dispersion of the carbon nanotubes. And then we can say the same thing, considering that, as we said before, carbon nanotubes can behave as a piezoresistive material, so we can incorporate them, and also Gabriele has shown to us many times during his presentation, but we can use then the carbon nanotubes dispersed into the cementitious matrix as a strain or a stress sensor. Again, if we have a system that is not correctly dispersed, so if we have some CNT bundles there, the gray area you have here, then if we consider this cementitious system, which is then submitted to a compressive load, of course all the system will be compressed, and of course the CNT bundles will be compressed at the same time. But what can happen then when the load will be removed is that the system, in this case the CNT bundles, will remain compressed, and they won't get back to their initial original size. This will be a problem, of course, because you will see, for example, as soon as the load will be applied again, you should see a progressive drift in the signal base of your material. So this is, of course, something not so good to see in a sensing system, because you would like that the system recovers the initial resistance or impedance value after the load has been removed. In this case, this cannot happen, because once these bundles have been deformed, they won't recover their initial size. And in addition, considering the volumes they occupied before applying the load, what can happen is that you can also have the presence of some voids that will remain in the system. And then, of course, this will also limit the mechanical properties of the CNT cementitious system. So again, also for sensing applications, a correct dispersion of carbon nanotubes is important, as we have seen, for the mechanical properties. So why do the CNTs tend to agglomerate? But of course, this is due to their very small size. Here we have a scanning electron microscopy image where you can see there is a strong agglomeration of the CNT bundles, and you can imagine that it won't be so easy to try to separate all the nanotubes each other. So in fact, this is due to the large specific surface area of this small object, and because of the high aspect ratio. At that point, considering the small size of this object, the van der Waals forces are important, and they tend to make these CNTs to agglomerate. So this is why we need then techniques to separate the carbon nanotubes, and there are, to this aim, some physical and some chemical methods that were studied. So let's start first with the physical methods. Among them, and we have seen also from previous presentation, that it's possible to use sonication to separate the carbon nanotubes, but it is not the only one technique. You can also ball mill the ceramic nanotubes to separate them, and also you can use a mechanical mixer to separate again the carbon nanotubes. And you can also combine different techniques together. So let's start first to talk about the sonication. You know all the ultrasonic bath, because there is almost an ultrasonic bath in, let me say, almost any laboratory, just for cleaning, for example, any kind of object you want to clean. But there are also more powerful devices, like, for example, the ultrasonic probe, which is a system that you can immerse in a liquid, and in particular, the tip of the sonic probe is immersed into the liquid you want to disperse, and it's a very powerful system. So how sonication works? Well, in fact, it is based on a piezo-resistive material that emits ultrasonic waves. And during the formation of these waves that are traveling into the liquid, there will be a cavitation field that will be created. This cavitation field will produce many small bubbles that will then implode, and when these bubbles will implode, they will create shock waves that will be able to deagglomerate the different bundles of carbon nanotubes, or also graphene, or whatever material you want to deagglomerate. It's also a system that is used for the production of ceramic slurries. If you want to disperse ceramic powders into liquids, you can use also this kind of sonic probe. Then the system, as I said, it's much more powerful with respect to the sonic bath, and it's of course more efficient. So the parameters you can control by means of these two systems is the amplitude of the vibration and the cycle, because usually you don't use the sonic probe in a continuous mode because it tends to heat the solution, and so you have to prevent the evaporation of water, especially for cementitious materials, because we know that the water to binder ratio is very important, but also for ceramic slurries, because at that point it's the solid loading which is an important parameter. Then how do we proceed? Of course, we start by introducing first the liquid, so the water in our case. We put then a dispersant, or a super plasticizer, as we call them in the cement chemistry. Then at that point we add the carbon nanotubes. We mix together, all together, these ingredients by means, for example, of a magnetic stirrer, and then we can continue using the magnetic stirrer by using then the sonic probe that can be immersed into the system, and at that point we can separate, or we can expect to separate the carbon nanotubes. Here, in some studies, the power necessary for the agglomeration of the carbon nanotubes has been quantified, and it seems that 70 watt is needed for separating the carbon nanotubes. And here, as you can see in this last image, you have some dispersions that were done, and of course this let me say, in this tube where you have a darker solution, is in this case the dispersion is optimum, because of course respect to the previous system, I don't know if you are able to appreciate it, but anyway, you can see that the dispersion is not correct, because some big agglomerates are quite visible in the different solution there. And of course, the fact that the solution is darker respect to the previous one, considering of course the same concentration of nanotubes that were dispersed in all the tubes, of course it means that if the solution is darker, the dispersion was better, because we were able to separate in an efficient way the carbon nanotubes. But we will talk later about the test we can do to evaluate the dispersion. Then, of course, at that point, one important parameter is the time. We apply the sonication, just because if we, of course, if the time during which we sonicate the system is too short, of course the dispersion won't be optimized. And at the same time, if the treatment will be too long, of course this is a waste of time, and of course a waste of money. But also there is the risk that nanotubes will be damaged, because the sonication, as I was mentioning before, because of the cavitation field and because of the energy which is released into the solution, if we insist for hours and hours of sonication, there is the risk of breaking the carbon nanotubes. So of course this is something we have to avoid, and so there is of course a certain time which is needed during which the sonication has to be applied. Here, for example, in this paper, the authors compared free sonication time, 30 minutes, 1 hour, and 1 hour and a half, and they considered that after 1 hour the power was almost constant, and if this time was increased above 1 hour, the power remained constant, and so the quality of the dispersion was not improved anymore. So in this case, 1 hour of sonication by means of a sonic probe was enough, and it was not necessary to insist for a longer time. Then you have here the effects of this sonication time onto the cementitious materials. They investigated different superplasticizers, so I won't at the moment detail them. We will talk about them later. They incorporated different amounts of carbon nanotubes from 0.06% up to 0.1%. No, sorry. They use different amounts of carbon nanotubes from 0.02 weight% and up to 0.3 weight%. The optimum amount was, on the contrary, 0.06 and up to 0.01%, because you have here then the tensile strength that was measured on the different samples, and as you can see, the highest bars were reached, for example, with 0.06 weight%, where the tensile strength reached 5 megapascal, for example, or it was above 6 megapascal with 0.1% addition of carbon nanotubes. Then if the content of the nanotubes was increased, the tensile strength was a little bit slower because it was close to 5 megapascal. So these results were achieved considering the different superplasticizers that were used, and in particular with this one, which was just Arabic gum. The dispersion was good, and of course this influenced positively the mechanical properties, in this case the tensile strength, that was higher because of the good dispersion. Then the second physical method is a mechanical dispersion. In fact, what happens is that it is important to apply a large shearing force, which is able then to separate the different nanotubes that are agglomerated. And so this shearing force can be applied by means of mechanical friction, collision, and crashes. It depends on the system used. For the nanotubes, because the systems that are used are the high-speed ball milling and mechanical agitation. So high-speed ball milling is a system where you have, as you can see, a strong oscillation of the system, and also there is an amplitude because you put into a jar with some balls the nanotubes and of course the water, and the system is shaped at a high frequency and with a certain amplitude. Unfortunately, you don't have to use this system for a long time because the nanotubes can be severely damaged if you insist with this treatment. So they will be shorter and shorter. And then the other possibility for the last physical method we can use is the mechanical agitation. So you can just have a blade that is rotating onto a rotating system, an agitator, and you have at that point also you create a shear force that will deagglomerate the carbon nanotubes. There are some high-speed shear mixers also that can be used, and as you can see, they can have a high rotating speed too. So these are the common systems used for dispersed carbon nanotubes. Then there are also other techniques that were studied if you look at the literature, and for example, different authors investigated the possibility to grow inside onto cementitious, onto cement particles or onto supplementary cementitious materials. They grew directly the carbon nanotubes. And at that point, you avoid the step of dispersing the carbon nanotubes as we have seen previously, but you have directly them incorporated into either the cement grains or the supplementary cementitious materials. And for example, one of the techniques that was used for growing these carbon nanotubes is chemical vapor deposition, or CVD. It is also known as hydrocarbon gas pyrolysis. So how does it work? Well, if you use the cement grains or if you use the supplementary cementitious materials, what is important is that you have some phases, like for example iron oxide, which is able to catalyze the carbon nanotubes growth. And this happens in a furnace, which works, of course, under a protected atmosphere. So usually it's nitrogen. A certain amount of CO2 is also used, and the carbon source is acetylene, which is injected into this reactor. Then at that point, because of the high temperature, as you can see, the system works in the range between 400 and 700 degrees. At that point, there will be the cracking of the hydrocarbon, so the acetylene, and the carbon atoms will grow directly onto the cement grains or the supplementary cementitious material. And in this case, they made the carbon nanotubes growing onto a sulfate-resistant cement. And you have here some SEM micrographs of the nanotubes grown directly onto the clinker, or here you have the carbon nanotubes that were grown onto silica particles. You have there the small silica particles, probably, let me say, silica fume, for example, considering the size of the silica particles. So it was an effective technique to grow directly the carbon nanotubes to avoid the dispersion step, and also if you think, for example, to the use on site of these carbon nanotubes, you also have the problem of handling these carbon nanotubes outside, and so of course for some safety reasons it's not so good. In this case, the carbon nanotubes are directly grown, and so they are entrapped in the different cement grains or SEM grains. Then here, after they made these growths of carbon nanotubes, they incorporated, they made the CNTs grown onto cement grains, and so they incorporated these materials. And they investigated, the authors of this review, they investigated the compressive strength of the obtained material. And as you can see, respect to the reference material that didn't contain any carbon nanotube, or respect to the second material there, which contained carbon nanotube that were directly, in this case, not grown, but they were mixed into the cement phase, and they used just a blade for mixing the carbon nanotube that were added into the mix. And as you can see, the dispersion in this case was not so good because the compressive strength was a little bit lower, 22 megapascal instead of 25. On the contrary, as you can see, the mechanical strength was much higher if the CNTs were grown directly onto the cement grain. And we can draw the same conclusion for the electrical resistivity of the material, but was good in case of a direct growth of the CNTs onto the cement grains. Then another possibility, again, to grow directly the carbon nanotubes into the cement grains is to use a microwave oven. In this case, the cement grain is coated first with a conducting polymer, and onto this conducting polymer, a catalyst is added, and in this case they use the ferrocene, and then they put the powder, which was treated in this way, into the microwave oven. Then the temperature rose up to 1100 degrees. The ferrocene decomposed and it became an iron catalyst for the growth of the carbon nanotube, and the source of carbon was at that point the polymer that was decomposed also, and the carbon nanotube grew directly onto the cement grain. So this was also another. This was a simple way, to grow carbon nanotubes onto cement grains. And here, as you can see, you have the microwave growth of the CNTs, in this case onto fly ash particles. And as you can see there on this low magnification SEM micrograph, the particle of fly ash was fully covered by the carbon nanotubes. So again, the dispersion was easier respect to the mechanical dispersion you have to do. Then we have talked about the sonication. So sonication can be an effective solution for dispersing the carbon nanotubes, but the problem is that once the sonication stops, and if we keep at rest the solution for a certain time, there can be a re-agglomeration of the carbon nanotubes. So just because, of course, the van der Waals forces are still active, they are still present, and so the sonication by itself is not sufficient. We need to use some dispersants. We need to use some surfactants that are adsorbed onto the surface of the carbon nanotubes, and at that point the sonication becomes more efficient, because you can keep at rest the solution and you will limit the re-agglomeration of the carbon nanotubes, because the surface of the carbon nanotubes will be covered by other molecules that will limit the re-agglomeration due to van der Waals forces. So this is one possibility, the fact of using dispersants or surfactants. This is not the only one, and for example with carbon nanotubes, other solutions were also investigated, and these solutions belong to the chemical methods. And for example, these chemical methods had covalent bond on the side of the carbon nanotubes in order to improve the wettability of the carbon nanotube. For example, among the different groups that can be attached on the side of the carbon nanotubes, these are, for example, hydroxyl, so OH groups, or carboxyl groups, COOH, or carbonyl, CO groups, that can be fixed laterally on the surface of the carbon nanotubes. And then these groups are not only positive to avoid and to limit the re-agglomeration of the carbon nanotubes, but they are also effective because they can create strong bonds with the cementitious matrix. So they will create strong bonds with the matrix, and of course the transfer of the load from the nanotubes to the cementitious matrix will be more efficient. So this functionalization of the carbon nanotube will be very useful. And for example, one classical functionalization of carbon nanotubes consists in forming carboxyl group along the side of the carbon nanotube, and this can be reached by using a mix of pure nitric acid and sulfuric acid in a 1:3 volume ratio. The functionalization must be done at 80 degrees, and it takes about 3 hours. So of course it's quite strong treatment. You have to take also some precautions, because you have to use pure acids. So of course you have to do this operation in safe conditions. And of course it's a quite drastic treatment, because it creates not only COOH group on the side of the carbon nanotubes, but these nanotubes are also damaged. So in some parts of the tubes you will see some carbon atoms that will be removed, and so there will be some holes along the sides of the carbon nanotube. But this is a classical functionalization treatment that can be done on carbon nanotube. And as I was mentioning there, here you have the carbon nanotube that was functionalized, and you have these COOH groups that are laterally fixed onto the carbon nanotube, and of course this will favor the growth of the cementitious hydration products that will form after the addition of water onto the cement powder. And of course you will have a strong binding of the carbon nanotube to the matrix, and this will of course increase the mechanical strength of the cementitious system. And then to convince you more, you have here in this table the reference system that doesn't contain any carbon nanotube, and in all the other materials that were investigated by these researchers, the system contains from 0.1 to 0.5 weight% respect to cement of carbon nanotube, and as you can see, the compressive strength increased significantly without the use of a superplasticizer that further increased the dispersion of the carbon nanotube, or if a superplasticizer was also added, the mechanical strength, the compressive strength, increased even more respect to the system where the nanotubes were used without any superplasticizer. So if you combine both, either the functionalization of the carbon nanotubes to prevent agglomeration, and if you use an effective superplasticizer, as you can see, you can obtain a significant improvement of the compressive strength and also of other mechanical properties of cementitious systems. And in this case also they compared the flexural strength, and again there were significant improvement in the flexural strength if you use the superplasticizer or if you don't use. But anyway, because of the functionalization, it was easier to disperse the carbon nanotubes into these systems. Then the last functionalization that was mentioned in the literature. Of course, I don't consider this review as a complete review on this topic. It was just because of the available time to give you some flash of information. So if you are interested or if you are working in this topic, of course, there are other papers, but I selected some of them just to give you an idea, an overview on this topic of the dispersion of carbon nanotubes. So the last treatment I found was a combination of treatment by means of ozone of the carbon nanotubes, followed by functionalization with soda, so NaOH, quite concentrated solution. And this treatment was lasted for about 24 hours. And then at that point, the so functionalized carbon nanotubes were dispersed into cement by means of a superplasticizer produced by the company Sika. And they used also ultrasound, an ultrasonic probe to disperse the carbon nanotubes that were functionalized into the cementitious material. Then they analyzed also, first of all, as this treatment with ozone and soda was a quite new treatment. They analyzed how many groups were attached onto the carbon nanotube. So this is why they made the dosage of the carbon content and of the oxygen content. Of course, the higher the oxygen content and the stronger the functionalization. This means that you have more carboxylic groups that are attached onto your carbon nanotubes. So it was for this authors a way to validate the efficiency of the treatment they proposed. And it worked in the case of the combination of ozone, either alone or ozone followed by soda treatment. And then if we look at the compressive strength, as we can see there, for the system without carbon nanotubes, the compressive strength after 28 days of curing was equal to 51 megapascal. And then for the systems that contained carbon nanotubes, as you can see, the compressive strength was almost not so significantly increased, even with the treatment based on ozone and the soda. So there was no significant modification of the mechanical properties of cement paste in this case. But they used also the materials they produced as self-sensing, for obtaining self-sensing cementitious materials. And for example, if you compare the response of the system which contains carbon nanotubes but non-functionalize them, as you can see, you have here in red the repetitive compressive stresses that the material, the sample had to withstand during the test. And you have the response of the piezoresistive system in black, and as you can see, there is a drift of the baseline of the response of the sensor. And this drift is due to the poor quality of the dispersion of the carbon nanotube. And on the contrary, if you compare the response of this system with the response of this system here, where they use the carbon nanotubes functionalized with ozone and soda, the response of the sensor in black is maybe lower respect to the previous system where the carbon nanotubes were not functionalized. But as you can see, there is no more drift of the baseline, and the response of the sensor is repeatable. So this is also an important feature for a sensor to have a certain repeatability over time, and of course there is no drift. And finally there you have the response of the system where the carbon nanotubes were functionalized with the mix of sulfuric acid and nitric acid, and as you can see, the response was good. There is no drift of the baseline, and also the response is higher respect to the last system based on functionalization of ozone and soda. Anyway, the functionalization in this case clearly improved the strain sensing performance of the materials prepared by these authors. So there is another possibility for the functionalization of the carbon nanotubes. We have seen that with the acid solution we can covalently bond carboxylic groups onto the surface of the carbon nanotube. The other possibility is to, at that point, for again avoiding agglomeration of the carbon nanotube, is to encapsulate them. So at that point, what can happen is that we use surfactants that are adsorbed on the surface of the carbon nanotubes and they encapsulate it. Usually the surfactants have an hydrophobic part which is adsorbed onto the carbon nanotube, and there is on the other end of these molecules there is an hydrophilic group which is of course which facilitates of course the dispersion into water. And these systems can be used of course on not only on carbon nanotubes but carbon fibers. They can be used also for graphene and also for any kind of material you want to disperse it. These kind of surfactants are also used with ceramic powders, for example, if you want to prepare ceramic slurries. So they are efficient and they favor dispersion of, in our case, carbon nanotubes into cement powder and cement suspension. Of course, you have to take care when using this kind of surfactants of the possible interaction with the hydration products of cement, because some of these products are very efficient. Of course, you have to take into consideration that once you dispersed correctly into water the carbon nanotubes, your work, if you work with cement, your work is not finished, because then you have to take this solution and you have to add cement. So at that point, when you add cement, you want to avoid any, let me say, unfavorable reaction between the cement hydration products and your surfactant, and sometimes this can happen, and in particular the hydration reaction can be slowed down. So, and for example, with other surfactants, there is the problem of the production of foam. So, of course, you improve the dispersion of the carbon nanotubes into water, but then you create a foam into your system once you add cement, and then you will have air bubbles that will remain entrapped into your material. So, of course, you can have a good dispersion of the carbon nanotubes, but you will have also lower mechanical properties because of the defects you created. So, you have to take care and to check that your surfactant doesn't create any problem. And then one of the most commonly used superplasticizer, the ones based on polycarboxylate superplasticizers are effective either in the dispersion of the cement grain and also in the dispersion of carbon nanotubes. Then how to evaluate the dispersion? I think I have to reduce my talk. I was too optimistic. So how to evaluate the dispersion? Well, you can use, for example, UV visible spectrometers, just because there are some characteristic bands in wavelengths into which, for example, the CNT bundles are not active, and on the contrary, if you have well dispersed the carbon nanotubes absorb the wavelength into this range between 200 and 1200 nanometers, and in this way you will see in your pattern, in your spectrum, the characteristic peak of the deagglomerated carbon nanotubes. And here you have the picture of a classical UV spectrometer, a classical instrument for chemistry labs. And in this case, for example, I will show you the spectrum, the absorbance spectrum, for example, with functionalized carbon nanotubes, so F-CNTs, and for the same concentration of pristine carbon nanotubes. And you have here also, for a different concentration, you will have the different curves for different times of sonication. And what we can see is that, for example, if we consider this concentration of carbon nanotubes, after 120 minutes, we can see this peak, which is characteristic of a good dispersion, just because the absorption increased. And if you remember the pictures I showed you, where there were different tubes with the solutions that were sonicated, the darker the solution and the better the dispersion. So in this case, this is a good dispersion that was reached after 120 minutes. And of course, the authors of this paper verified that the mechanical properties were also good after this certain time of sonication. But also what they observed is that once you correctly disperse the carbon nanotubes into water, the work is not finished, because then you have to consider also that you will add then the cement powder to your dispersion, and you have to verify also that the solid phase addition, so the cement powder addition, will not perturbate your system, and you will also have in the hardened cementitious material a correct dispersion of the carbon nanotube. Then another possibility for evaluating the dispersion into the solution is the use of another instrument, which is dynamic light scattering, just because, you know, carbon nanotubes are very small objects, so they are moved by Brownian motion, and this Brownian motion causes dynamic light fluctuation, and this can be checked by means of this instrument, which is the DLS, the dynamic light scattering. So it's possible to evaluate the dispersion by means of this instrument, but also the diameter of the particles. And of course, the smaller the diameter of the particles in your solution, and the better the dispersion. And in this case also, a comparison was done between carbon nanotubes added into water and dispersed into water, but without any surfactant. And of course, the particles were much bigger respect to the addition of any of these surfactants that are mentioned there. And of course, in this case, the particles were much smaller, which is an indicator of the good dispersion. And of course, this was also reflected on the mechanical properties. And in this case, the mechanical properties were lower, because for some of them, there was the creation of a foam, and in particular, SDS, sodium dodecyl sulfate, is a common surfactant that tends to create foam. And of course, if you use a foaming agent in your system, the compressive strength will be, of course, lowered. So this is why you have to take care in the surfactants you use if you want to disperse these carbon nanotubes into the cementitious system. And then just a few words about the zeta potential, which is the potential between the particle into the suspension. This particle into suspension tends to, of course, agglomerate electrical charges onto its surface, and you have the creation of two layers, one layer which is fixed directly onto the surface of your particle into the water, and this layer is fixed, and you have then a diffuse layer around this first layer, and this layer is not fixed in the same way, and when the particle moves, this layer is able to be deformed because of the movement into the solution. And so if you measure the potential between the surface of your grain and the limit of this diffuse second layer into your particle, you will have then the zeta potential. So again, there is an instrument which is able to measure this zeta potential. And of course, again, if you measure the zeta potential, and if you have already done it, you know that when the absolute value of the zeta potential is above 30 millivolt, this means that your suspension is stable, and this means that if you put the suspension at rest, you will observe the sedimentation of the particles in a long time. Of course, the zeta potential depends on the pH of the solution, and it can change. It can be reduced, or it can increase in function of the pH of the solution. And again, they functionalized the carbon nanotubes there, and they verified that the suspension was stable because they measured the zeta potential of the suspension, and of course the compressive strength was higher respect to once the system was stable, once the carbon nanotubes were functionalized, and the zeta potential was correct, above 30 millivolt, and they observed higher mechanical properties with respect to the reference sample without carbon nanotubes. Then you have here, just for the sake of information, the different dispersion methods we have discussed. In this review, the authors considers the different technique. As you can see, the ultrasonication is the preferred technique for the dispersion, followed by the standard mixer, but there are significantly lower amount of papers where they use the standard mixing system for dispersion of carbon nanotubes. And then you have the pros and cons of the different solutions. Here there is one solution that I didn't mention because it is used for polymers mainly, where you apply an electric field that moves and orients the different carbon nanotubes into the polymer, and this is why I didn't mention it. But anyway, more or less you have here the pros and cons we discussed previously. As my time is running, so I have to close. And then to conclude, yeah, we have seen many different dispersion methods. Unfortunately, there is no ideal solution at the moment, even if we combine together different techniques. So there is still the need for the improvement and the optimization of the dispersion, because there are still on the table some problems due to the poor dispersion and the low dispersion efficiency. So there is still work to do, so which is good for you working in this field, because you have the possibility to do some original works. And also there is also the need to explore new dispersion, not only processing, but also characterization techniques. So thank you very much for your attention.